Howdy there, y'all. Today, I wanted to go over foam cells and the development of atherosclerosis. Right now, I want to start off with some words and definitions. I want to tell you what they mean in the sense of this video, foam cells and atherosclerosis, and then I want to get into the visuals afterwards. It'll just make everything a lot easier, okay? So, platelet-derived growth factor. The primary thing we want to focus on that platelet-derived growth factor does is migration of smooth muscle cells, right? Normally, smooth muscle cells are in the tunica media, the middle layer of the vascular wall, and they're going to, in the setting of endothelial injury, they're going to migrate using platelet-derived growth factor to the site of injury and form a fibrous cap, right? Now, how does it form that fibrous cap, right? So, first and foremost, you have to have activation of certain cells in order to produce platelet-derived growth factor, right? All right. So you have activation of endothelial cells. Once you have endothelial injury, right, you're going to have release of endothelin from neighboring healthy endothelial cells. This is going to cause local vasoconstriction, right? This vasoconstriction is actually going to allow a decreased amount of blood to flow through that vessel, allowing for the activation of our next cell types, which are platelets. These form the primary plug after the endothelial injury. Think about it like this. We have two arteries, one straight and one bent, right? Now, this artery is just normal, right? We're not gonna say it's vasodilated or anything. Let's just say it's at its normal baseline, right? And we have to knock out these cells due to endothelial injury. So these cells, if you look at it, right? These cells that are knocked out for the sake of the video are the same number of cells. But this one, where it's not vasoconstricted, will just be a lot more time for and a lot more platelets to come in and fill that area, right? But if you have something called reflexive vasoconstriction, right? This is kind of like a bending of the artery or arteriole and a narrowing of the lumen produced by the endothelium and other products, which actually decrease the amount of space that the platelets have to fill up in order to fix this, right? So, after the platelets come in and they fix this, they're releasing platelet-derived growth factor along with the endothelial cells, and then these smooth muscle cells, down here, blah, 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 end up migrating here and starting to form the fibrous cap, right? Just to make sure that there is no leakage between the vascular space and extravascular space, right? So, what is the last cell that does this, right? One of the major cells in the foam cell, it's actually an activated macrophage. Macrophages will also produce platelet-derived growth factor, furthering lead to the migration of these smooth muscle cells, right? Let's get into transforming growth factor beta. Now, we know transforming growth factor beta as a anti-inflammatory cytokine. It is normally used in the setting of healing with fibrosis. But tumor growth factor beta, I guess in that same arena, is going to lead to differentiation of these smooth muscle cells after they have migrated, right? And they're going to differentiate into myofibroblast-like cells, right? What do you know about myofibroblast, right? They're like fibroblasts, but they have contractile properties, right? What they're gonna do is they're going to produce collagen and elastin. These will help secure the fibrous tissue forming the cap, allowing it to hold a lot more of that necrotic debris than it previously would have before it was a myofibroblast. right? Now, this one is going to be easy. MCP1, it might be MCP8, but I think it's MCP1, which is monocyte chemoattractant protein. This will attract monocytes into the area of inflammation using this as well as various chemokines like IL-8. And once these monocytes travel into tissue, they differentiate into macrophages. That's the only difference between monocytes and macrophages. Monocytes are in circulation and macrophages are in tissue, okay? So once these platelets form the clot, these macrophages will move into the tissue, into the wall, and then, or these monocytes will move into the tissue, into the wall, and then become macrophages in the tissue, okay? Now, for tumor necrosis factor alpha and IL-1 beta, I grouped them together in this one because they do a lot of similar functions within the body, some of which is they promote sleep as well as fever induction, right? But in the sense of foam cells and atherosclerosis, or in the sense of vascular alterations in general, right, it's going to cause a few different things. The first being increased vascular permeability. Might seem pretty self-explanatory, right? Increased vascular permeability. This will actually allow these monocytes and macrophages and neutrophils to move through. It actually allows for diapedesis or extravasation of these leukocytes into the tissue from the vascular space, right? Another thing that actually helps that diapedesis or extravasation is increased expression of integrins. It'll actually do this to integrins and selectins. So you got your VCAM and your ICAM for integrins, and your P and E selectins for the selectins, right? And then one more key feature that I want to bring up for that, it's not necessarily vascular changes, but it actually leads to increases of IL-6 levels. Now, this is important. These two molecules will induce IL-6. What does IL-6 do? IL-6, to be as simple as possible, IL-6 works on the hepatocytes, right? They induce hepatocytes to produce acute phase reactants, APR. Now, we've heard of all these acute phase reactants, right? Let me give you a couple. Procalcitonin, hepcidin, haptoglobin, ferritin, fibrinogen, alpha-1 antitrypsin. There's something that I want to focus on for this video, serum amyloid A, or SAA. And I'm gonna go over that a little bit later when I talk about LCAT, all right? Let's get into CETP, all right? So what is CETP? CETP is cholesterol ester transfer protein. Now, one thing I want to talk about really quickly is the function of cholesterol ester transfer protein in the simplest terms possible, right? We're going to talk about the cell types next. But cholesterol ester transfer protein is going to exchange triglycerides from one lipoprotein particles with cholesterol esters from another lipoprotein particle. Now, what are these lipoprotein particles that I'm talking about? This one that has the triglycerides is VLDL. The one that has the cholesterol esters is HDL. And this CETP right here between them is actually going to take triglycerides from VLDL, put it into HDL, and then it's going to take cholesterol esters from HDL and put it into triglyceride or VLDL. Isn't that fascinating? Right? If you know anything about chylomicron and lipoprotein assembly, you know that the denser they are, the smaller they are, right? So chylomicrons are the largest lipoprotein particle. HDL is the smallest lipoprotein particle. And that's why it's high density lipoprotein, right? So what makes it high density? It's these cholesterol and these cholesterol esters. That's what makes it high density. So the more cholesterol esters you have, the more mature your HDL is. That's the more cholesterol that it can take from peripheral tissues and put it back in the liver to be excreted into bile, right? So same thing goes, if you have less cholesterol esters, your HDL is immature. It has less of an ability to exchange cholesterol in peripheral tissues, right? So on the opposite side of the spectrum, VLDL is more dense with cholesterol esters. So what does this mean? This CETP is going to change this VLDL with these cholesterol esters into LDL or IDL type particle, and then these triglycerides and loss of cholesterol esters, it's actually going to turn this HDL into immature or nascent HDL, right? Let's talk a little bit about LCAT. All right, LCAT is lecithin cholesterol acyltransferase, right? Just plain and simple. What's its function? Plain and simple. Its function is uptake of free cholesterol, free floating cholesterol in the blood, right? That's what we're talking about. In peripheral tissues, all of that. It uptakes free cholesterol and converts it into cholesterol esters. Do it up here. This is going to be our HDL molecule. This is going to represent other cells, right? We could say it's macrophages, we could say it's endothelial cells, other cells, okay? Now, you have this LCAT. You have this LCAT protein right there on top of the HDL. You have this LCAT protein on top of the HDL, right? It's going to take in free cholesterol, turning it into cholesterol esters, right? And, you know, let's just say that this is the cholesterol coming in, right? The purple right there. And then the brown is going to be the cholesterol esters. Okay, what do you notice about the distribution of the cholesterol esters? They're in the center of the HDL particle, right? And that's because they're the most hydrophobic, right? They're the densest, but they're also the most hydrophobic. So they're going to be concentrated in the center. Whenever you turn cholesterol into cholesterol esters using this LCAT, it's going to migrate to the center because of how hydrophobic these esters are. Where LCAT binds, right? Where does LCAT bind? I know it binds on HDL, but it actually binds onto a specific place on HDL. LCAT binds the ApoA1 protein receptor on HDL. So LCAT is bound to ApoA1, right? Why is this significant? Okay. Why is this significant? I'm gonna tell you why. ApoA1 Normally binding LCAT is actually the spot where HDL binds to the macrophage receptor ABCA, ABCG1, or on endothelial cells, to take the cholesterol from those cells and then deposit it back into the liver after a few trips to the blood, right? So the macrophages bind this ApoA1, right? These cells bind this ApoA1 in order to do that. So if you don't have this ApoA1, if it's non-functional, then these HDL cannot take in these cholesterol because this LCAT will be wiped out. It will be non-functional, right? Now, what would cause an ApoA1 to not be there, to not be functional, right? I'm sure there's some mutations you guys could talk about, right? But let's talk about it in the setting of inflammatory processes. Let's go back to this IL-6. Remember I told you I wanted you to pay attention to this SAA? So this SAA with HDL is gonna do a big thing. It's gonna do, honestly, it's a horrible thing to HDL, but it's crazy to think about. This SAA is actually going to displace this ApoA1, whatever you wanna call it. It's going to knock that thing out the way, okay? It's gonna do that. And then after it knocks out the ApoA1 out the way, it's just gonna stay there, right? This SAA molecule is just gonna stay there. It's completely displacing and knocking out the ApoA1, making it non-functional. So this ApoA1 not being there, it prevents LCAT. So it prevents mature HDL formation. It prevents uptake of cholesterol from the HDL, further preventing mature HDL formation, right? Because not only do you not have LCAT, so you can't form cholesterol esters from free cholesterol, but you can't take in the free cholesterol. So, I mean, it kind of makes sense that this wouldn't be functional, but you know, you're just messing up the whole process, right? Just by having serum amyloid A being produced. Last thing I want to go over here is the function of tumor necrosis factor alpha, IL-1 beta, and IL-6 on cholesterol ester transfer protein and lecithin cholesterol acyltransferase. Okay, so cholesterol ester transfer protein would be decreased, right? Now, if that would be decreased, that would mean more HDL would have their cholesterol esters, right? That's good, and that is actually really good. In an inflammatory condition, this is a protective mechanism. This allows HDL to retain their cholesterol esters in the setting of them not even being able to absorb them. So they retain it, further, you know, potentially staying as mature HDL or just not losing any more of their cholesterol or esters that they already had. Now, LCAT, it's also going to be decreased. And I mentioned the mechanism for that, right? And this is not protective, this is destructive, right? Because you're not allowing the uptake of free cholesterol, or you're not allowing the conversion of free cholesterol into cholesterol esters. You're not allowing the conversion of the cholesterol you already have present into cholesterol esters, right? This ApoA1 disappearance messes all that up, right? So this is a destructive mechanism, decrease LCAT, but this is a protective mechanism, decrease CETP, right? And it's caused by these three cytokines, all right? So that was it for this part. I'm actually gonna go into some visuals, so if you'd love to bear with me, I'm gonna show you guys how it gets done. Hey y'all, this is the second part of foam cells and the development of atherosclerosis, all right? It's gonna be the visual. Now, you end up with a normal arterial, right? Normal artery, normal arterial. And say you have hyperlipidemia, maybe toxins in your blood because you're a smoker, or you have uncontrolled diabetes, right? You can have high glucose levels. Let's just say these light blue are the toxins and they're gonna target this endothelium, right? And as it targets this endothelium, it's going to injure it, or it's going to damage or kill it, right? So you knock out these cells. Well, in order to take up that debris, you need some neutrophils, right? I'm gonna do this with the big N in there, right? So this is neutrophilic infiltration, right? To pick up that debris of the dead necrotic cells, right? And with that neutrophil infiltration and the death of these endothelial cells, you actually have production of endothelin from these healthy cells. Endothelin would cause something called reflexive vasoconstriction. That's when you're kind of bending the artery and narrowing the lumen in that area to prevent the consumption of excess platelets to fill this otherwise wider gap, right? If you think about it like this, think about it like a shape like this, right? If you kind of bend these inward, right? That's kind of a bad example, but if you kind of bend these inward, this gap gets smaller, right? And it's the same thing for these, right? On top of that, simultaneously, you're gonna have production of platelet-derived growth factor and transforming growth factor beta. But this neutrophil is actually gonna release chemokines, right? It's gonna release chemokines, it's gonna release cytokines like tumor necrosis factor alpha, IL-1 beta. Its purpose is to attract more white blood cells or leukocytes, but also to increase vascular permeability and upregulation. So this neutrophil is actually going to produce tumor necrosis factor alpha, IL-1 beta, and IL-8. Now IL-8 is a chemokine. I think it's the same thing as saying CXCL8, right? It's a chemokine. It attracts other leukocytes to that area, right? Because this is an injury here. Now, tumor necrosis factor alpha and interleukin-1 beta, these will actually cause increased vascular permeability, plus they'll also cause increased upregulation of integrins, right? ICAM, VCAM. Now, vascular permeability happens fairly quickly, but this integrins actually takes a little bit longer. You actually have to take time in order for the ribosomes to produce those proteins, right? So it tries to call in these other leukocytes, but they can't move in quite yet because before they can even reach it, these platelets are already coming in the dark blue. They're already coming in. Platelets are already coming in. So by the time we're over here, these platelets are already activated and filling this gap with this vasoconstriction, right? But what do platelets produce? Platelets produce platelet-derived growth factor, but they also produce transforming growth factor beta, just like the endothelial cells, right? So this platelet-derived growth factor is actually going to cause these smooth muscle cells to migrate. And it's going to migrate to try and form a cap above this clot, because clots can embolize, and you don't want that. So it's a protective mechanism to release this platelet-derived growth factor, right? But this transforming growth factor beta also transforms these smooth muscle cells into myofibroblasts, producing the collagen and elastin, allowing it to stay sturdy and kind of stretch if that core ends up getting bigger. After that's formed, after the fibrous cap is formed, right, due to the collagen and elastin, you don't have to worry about any blood leaking, any other inflammatory molecules leaking in there, right? Nothing that you don't want, especially. So what you're gonna do is these cells upstream, since blood flow goes this way down the artery, upstream you're gonna have production of nitric oxide, causing vasodilation, causing an increased diameter. This would lead to hemostasis, which means the blood cells, red blood cells, white blood cells, would be going through that section of the vessel a lot more slowly. This would allow for these neutrophils, macrophages, all these innate immune cells to come in there and take up any material that would be there, right? But earlier, these neutrophils came in there, right? So what else would be in there? But you gotta remember, it's not only leukocytes that go in there. It's red blood cells, but also there's other things in the blood. You got LDL that also comes in here. LDL sneaks in here during the initial injury. So there's LDL here, right? And the LDL here is being oxidized for various reasons, normally due to reactive oxygen species, which are normally formed in smooth muscle cells and endothelium, which can be released in the due to cell destruction or cell lysis, which was happening up here. But what happens? What attracts these LDLs, right? It actually binds to proteoglycans in this basement membrane, right? Remember I said it's the basement membrane. You can't forget about that. It binds to proteoglycans in the basement membrane, keeping it stuck, allowing those reactive oxygen species to work on it without the natural antioxidants present in the blood, like vitamin E and C, right? Or as well as glutathione. So these end up getting oxidized, releasing inflammatory particles, trying to attract more white blood cells. But now, think about it now, you've been having these integrins being produced, right? Got integrins with this slow blood flow. And what it's going to do is it's going to grab the neutrophils, it's going to grab the macrophages, it's going to grab all those phagocytic cells and push them in between the gaps in these cells due to tumor necrosis factors, increased vascular permeability, right? So it's going to push these, let's say, macrophages in here. These macrophages are actually going to sense these oxidized LDL particles via something called a scavenger receptor. These scavenger receptors actually take in that LDL, oxidized LDL, and it attempts to give it to HDL. Now, like we mentioned earlier, HDL in this situation wouldn't be functional, it'd be less functional. Now, these macrophages are going to bind these oxidized LDL via the scavenger receptor. It's going to internalize these oxidized LDLs, and normally it would attempt to pass it on to an HDL part, right? And it would do that via ApoA1 receptor on the HDL, and something called an ABCA1, ATP cassette binding protein A1, and in severe inflammatory states, chronic inflammatory states, both ApoA1 and ABCA can be dysfunctional. At the end of this video, which is soon, I'm actually going to talk about the cases in which you can have ABCA dysfunction, right? But for purposes like this, you remember that in this we produce IL-6, right? Tumor necrosis factor IL-1B would produce IL-6, right? Okay. So the IL-6 produced would actually produce SAA, which would knock this out, ApoA1, preventing efflux of cholesterol from these foam cells, right? So these foam cells are trapped, right? They're big, they're bloated, they can't fit through these even increased vascular permeable endothelial cells, right? And they keep, this is a positive feedback loop. These are going to be trapped, releasing a bunch of cytokines, right? These cytokines are going to leak out, and then it's going to cause this whole process to happen again. More macrophages to come in to take these oxidized LDLs, because these macrophages, they're gonna end up dying if they have nowhere to go. They can't push out that LDL, they're gonna end up dying and becoming a necrotic core, which is normal in atherosclerosis, right? But this is just gonna keep happening, and it's gonna keep going, and that's gonna get bigger and bigger. That fibrous cap will stretch and stretch till that elastin can't stretch anymore, and it's going to burst, and that's gonna cause spontaneous thrombotic occlusion of a vessel, right? So this is the end of the foam cells and atherosclerosis video. I just wanted to talk about causes of ABCA1 and ABCG1 dysfunction. I was gonna talk about something else, explain a little bit more, but lucky y'all, I'm not gonna do that. So first I want to talk about trapping of the cell. And this is done by cyclosporin A. And not necessarily trapping of the cell specifically, right? But it actually traps the ABCA protein or receptor. This prevents binding to HDL, specifically prevents ApoA1 binding, and decreases cholesterol efflux, right? And then you got the ones that are degradative, right? You have calpain mediated. And this is actually what I was going to explain. I'm not going to do that anymore. And then you have increased unsaturated fatty acids. Now, these are degradative, right? So these unsaturated fatty acids actually cause phosphorylation of a serine residue, serine, on ABCA1, making it functionally inactive, right? Now, well, targeting it for degradation. It's functionally inactive, then it targets for degradation because it's not doing anything, right? So, calpain mediated. Calpain, look at my video about IL-1, but it has to do with IL-1 alpha, and it actually causes cleavage of that under cell stress or increased calcium influx, right? So if you have cell stress and increased calcium influx, then calpain will activate and lead to ABCA1 degradation. There's 3 more things that I want you guys to know, and essentially it's alterations in the cell microenvironments. Alterations in the cell microenvironment actually consist of, 3 things that I'm going to talk about today, right? You got reactive oxygen species. You often have an acidic or a decreased pH. And a decrease in membrane fluidity. If you think about it like this, ROS and acidic pH are naturally in the atherosclerotic environment just due to its breakdown of other molecules, right? And decreased membrane fluidity, if you think about it like this, like all the cholesterol being deposited in there and or from other cells are being taken up by these foam cells in excess amounts. And since they can't release it to other cells and or HDL, it's going to cause decreased membrane fluidity. Because if you remember from biochem, cholesterol in the membrane, depending on the temperature, can increase or decrease fluidity. Okay? These two specifically just cause dysfunction. It just makes the ABC1 dysfunction of A, B, C, A1, G1, all that. And decreased membrane fluidity, this actually decreases the mushrooming effect. I'm going to do another video about ApoA1's binding to ABCA1 on endothelial and macrophages, but essentially it's a ballooning effect. And it's going to decrease that, which would lead or cause decreased cholesterol efflux. And all of these, since they're dysfunctions in the cholesterol efflux protein or receptor, they're all going to cause decreased cholesterol efflux. But alright, y'all, that was the end of the video. I know it was long. Thanks for bearing with me. Hope you guys learned a lot or enough to understand foam cells and atherosclerosis. But I'm out. Peace.